17.1, and we're near the end of this semester, and I think we're going to make it. This one is titled Several Variables. So now we have a complicated scenario of having variables represent independent items. So the idea of each variable representing an independent item. Okay, so if we're talking about a table, we would have, and then making chairs, well, those are two distinct items that each have a cost factor, and that's what we're analyzing. So to begin this section, we're going to expand our construction of functions that have more than one variable to consider in the production of a multi-products within a company. This is the inclusion of multiple variables in a function known as function of several variables. So I got this from the textbook. Expression is representing z as the function of several variables. And in this case, we have an f of whatever many variables we have, and z represents that item of two variables if the unique value of z is obtained from the second ordered pair of real numbers x, y. The variable x and y are independent variables, I mentioned that, and z is a dependent, the outcome of that variable. The set of ordered pairs are all reals, real numbers, big, can be decimals, can be fractions, can be whole numbers, negative, positive, such that f of x of y exists in the domain of f. The set of all values for the function xy is the range. In other words, anything we input as xy gives us the f of that xy. So we're going to start easy, of course. And we have this example. First is of using xy values to determine which is now f of xy. So our z variable is now f of xy. So, sorry about that. I need my glove, don't I? Let me get my glove. In this function, we have f of xy is equal to, in this case, we have 2x minus 9y plus a 7, So we're going to do our A1 first, which is the z, which is f of 4 and negative 1. So this means I'm going to have 2 times the 4 minus 9 times the negative 1 plus that 7. And then I'm going to have 8 plus 9 plus 7. Well, that gives me that f of 4 and negative 1 equals 24, doesn't it? Now you can use your calculator, but 8 and 7 is 15, and 9 makes it 24. Okay, well that's our A. Well, let's look at our B. Our B says that the function at negative 4 and 1. So this means that I'm going to have 2 times the negative 4 minus 9 times the 1 plus 7. And again, you can do this on your calculator, but this is a negative 8, a negative 9, and a 7. So we're going to have f of negative 4 and 1 to equal a negative, in this case, have negative 10. Negative 8 and 7 is negative 1, and negative 1 and 9 is that value. So now I'm going to do the C1, which is again building confidence on what we're getting. And we'll be doing this in our work. These are two negatives, negative 4 and negative 5. So let's see what happens here. All right, so I have 2 times a negative 4 minus 9 times a negative 5 plus a 7. This is going to give me a negative 8, a positive 45, and a positive 7. So I end up with 44 for the function insert of negative 4 and negative 5. All right. So now we're doing our last one of this one. And again, we're getting used to substituting our values for z in terms of f of x, y. And in this case, I have a 0. So I have a 2 times a 0 minus 9 times an 8 plus the 7. That is an 8. Yes. So that gives me 0, and this is a negative 72 and 7. So I'm going to get a negative 65 is the outcome for the function at 0 and 8 of two independent variables. Nothing hard, so here we go. On this guy, we have natural log. And we're doing the same processes except using natural log. For our a, I have f of 1 and 0. So I have 6e to the 0, to the 1, sorry about that. I got my x and y confused, didn't I? Plus ln of 1 plus 0. So that gives me 6e plus ln of 1. Well, ln of 1 is 0, so 6e is the value of f of 1 and 0. And you're given exact answers. Right. So now we're going to do our B. Our B says we're using f of 3 and negative 2. So I'm going to have 6e to the third plus ln of 3 minus 2. That means I'm going to have 6e to the 3 plus ln of 1, which we know is 0. Therefore, f of 3 and negative 2 is this exact answer. So now we're going to do our C. C is f of 0 and e. So that's going to give me 6e to the 0 plus ln of 0 plus e. All right. So this is going to give me 6, because anything to the 0 is 1, and this is ln of e. Well, these are inverses of each other, so I have 1, 6 plus 1. So I get 7 is f of 0 and e. Now my last one. This is 0 and e cubed. So I'm going to have f of 0 and e cubed equals 6 e to the 0, I love that, and ln of 0 plus e to the 3. All right, So this is going to give me f of 0 e to the 3 as 6 plus ln of e to the 3. Well, these are inverses, so I'm going to have 6 plus 3 equals f of 0 and e to the 3. 9. All right. In each case, we're learning the concepts of identities and input. All right. So now we're going to talk about graphing, and I only picked a couple, and the couple is only to explain a three-dimensional plane. And we're going to start right there. Because we have x, y, and z, we do z as the horizontal, the vertical rather. And we depict y as the horizontal axis. Now, the only reason we do that is to show the three-dimensional plane, okay, to display this in a form without having a three-dimensional axis. And then x is the diagonal. All right, so let's talk about that for a little bit. Let me get some kind of straight lines here. Okay, and then I'm going to have another one. And then my last one. So this is my, oops, sorry. This is my Z line, this is my Y line, and this is my X. It's positive to negative, and positive to negative, and positive to negative. All right, here we go. So we've got this function, x, y, and z equals 8. Very simple. So we first find their intercepts. So that means that if I'm looking for x, I'm going to have some number for x, 0 for y, and 0 for z. So I'm going to have x plus 0 equals 8. Therefore, x is 8. So I've got that intercept. Now I'm going to do the next one, which is 0 for x. We want to know the y, and 0 for z. Now you can see the pattern here. I know you can. So we're saying 0 and y and 0 have to equal 8. Y is 8. So we got that guy. Very good. Now we need the last one, which is our z. 0, 0, and our z. Right? So in this case, we're going to have 0 for x, 0 for y, and our z is 8. These are all our intercepts. Okay, so now we're going to graph it. In the graph, we would have our x is 8. 1, 2, 3, 4, 5, 6, 7, 8, right there. Our y is also 8. 1, 2, 3, 4, 5, 6, 7, 8. And our z is 8. 1, 2, 3, 4, 5, 6, 7, 8. And then we would draw our lines. Oops. We would have this area that would contain this function. And we would look for that area. And we notice that this is on the negative, positive, and this is on the negative. And so all of these are not correct. Look at ours. So it would be this one. You have two that I want you to graph, and they're not difficult, but they give you a perspective of what you're doing. So in this case, we don't have an x value, variable, I should say, not value, but we include it. We know it's always 0. All right, so I have 3y plus z equals 3. So I want the y, 0, y, and 0. So that means I'm going to have 3y plus 0 equals 3y equals 1. All right, that's my intercept. So then I'm going to have 0, 0, and our z. And in this case, I'm going to have 3 plus z equals 3. Z is 3. All right. So, and we know we have 0, 0, 0 for x. So this one has x. This one does not. And this one has, okay, because we want 0, 0, 3. That's a good one. And then we want 0 and 0, 1, 0, 1, 0. And so, which one is it? Okay. Um, oh, look at that. Sorry. This is at, so it's between these two. And I can't read, but 3 is right here. So that one is wrong. It is this one. That right there, I know you can't see it very well, but there is no 3 there. That's 2. And here we have 3 on that one. So this is our 0, 0, 3. And then we wanted 1. And this is at y is 1. Even here it's y is 1 right there. So it's that one. All right, now I have this that came out of the textbook, and I'm going to give you the answer to this question so that you'll know. In the context of functions of one variable, the vertical line test was presented to determine if the graph is the graph of a function. In other words, we know that if I have this, the one-to-one says, yes, for every x there is only one y. And then we would know that if it was this, it is not a function. All right, so that's what that is saying. In a one variable, y equals some mx plus b, or x squared plus some such and such, all of those variables. Okay. Does this test apply to functions of two variables, and explain? Well, two variables, more than two variables, two or more, I should say, create a volume experience. Um, and um, and look, it showed us some particular shapes, and I'm going to do one in the next problem. But the answer is, for the given endpoint, a point on an xy plane, the line which goes through the endpoint point is parallel to the x-axis and can be used in the vertical line test. If this line passes through the graph of the surface more than once, for any input, then the equation that represents a surface is not a function. So it's saying, okay, that yes, we can use it if it's parallel to that, to the z-axis. And these are parallel. This one is parallel, and this one is parallel. But we do have some scenarios like the one I'm giving you next, where it's not parallel. In other words, for every line we draw through the XY, we have several. Okay, so in this case, we're only going to talk about this particular one. There are 4 listed in the textbook, but this is the one I want to focus on. So this guy is a paraboloid. So it has a shape of a parabola rotated around the y-axis. And it creates this shape, the parabola does. So in this case, we're looking at the form z equals x squared plus y squared. So that we're saying that the f of xy equals this x squared plus y squared. Notice what we have. All right, that they are squared. So I've given you this guy here, and we notice it's in paraboloid form. But it's negative, which means it's flipped upside down. And it also has a fractional cut in 4 parts, making it wider. So we know it's not a sphere. And we know that it's not a cone. And here we see it flipped and adjusted for division of 4. So this is our answer. All right. So now we get to how do we apply this stuff. I only gave you 2 problems because it's just vital that you understand we can have more than one variable to explain something in a function. Here we have the labor described as the independent variable as $270 per each unit. Then we have materials, and that's RY, cost $143 per unit. And then we have something called capital. Now the capital is the cost for labor, administration, those things. We know it's 87 per unit. So they want us to write a function of total cost. Cost of x, y, z equals 270x plus 143y plus 87z. That's all you do. All right. And our last is a substitution, and I just found it interesting. So that's my fault that you have this one, but it's pretty interesting. It says an article explains the locomotion of different sized animals that can be compared if they have the same Frody number defined as F equals velocity squared over gravity, some kind of gravity, right? Yeah, gravity times the leg length. So in our A, they want us to use this formula. Different animals change from trot to gallop at the same time, at the same Frody number, roughly this guy, 256 hundredths. Find the velocity at this change occurs for an animal with a leg of 53 hundredths meter. So the leg isn't very long, is it? Okay, because a meter is a little bit longer than a yard. So this is a little half. So it's not a very long leg, but we're going to find out what the velocity is. So we have F equals velocity squared over gravity times the leg length. This number was given to us. And the gravity is in meters, 9.81. And the leg was 53 hundredths meter. So now we're going to cross multiply and get the 256 times a 9.81 times, and that's 0.53 has to equal velocity squared. So we're going to do that math first. And now I can't do that on my head. So here it comes. Well, so I'm going to clear that and put the 2 and 56 times the 9.81 for gravity per meter squared times the leg of 53 meters. And we get this number, 13, and I already lost it. Let me see what I can do here. Maybe always in front, so I can 13, 3, 1, 0, 2, 0, 8, it looks like. Yep. Okay, now that's for velocity squared. So we want to do second square root of this 13.310208. And I'm going to get this horrible number, 364,831, blah, blah, blah. And what we need here, if I'm not mistaken, is we need like 3 decimals is all we need. So we can do that. I've got my notes on that one. And no, it's 1 decimal. Sorry about that. So we're talking 3 6/10 meters per second is our velocity. All right. So now we're going to talk about our B. Our B, we're talking dinosaurs. An ancient footprints of a dinosaur are roughly 1 6/10 meters in diameter. So that's almost, yeah, that's pretty big, right? Uh, uh, more than a yard, like almost a yard and 3/4, corresponding the leg length of roughly 6 4/10 meters. By comparing the stride divided by the leg length with that various modern creatures, it can be determined that the Frody number for this dinosaur is 25,000. How fast is the dinosaur traveling? Well, we know that the gravity is in meters squared, so it's 9 and 81 meters per second squared. Okay, so we're going to find out what this dinosaur's velocity is. All right. So we're having this, and this is per second. Per second. That's the problem with visualizing how fast this is. So we have velocity squared over 9/8100 times that, oops, sorry, not the Frody number, I need the leg, which is 6.4. So I'm going to have times the 981 and the 640 equals velocity squared. handy dandy calculator. And let me move it out of the way. Here we go. And we're going to do the math. 0.025 times 9.81 times 6.4. And I get this number. Not very big, is it? Now we're going to take the square root. And we're going to get, oh, I made a bobo. I am so sorry. Second square root of 1 and 5, 6, 9, 6. So this is going to be 1.225, 828, etc. equals velocity, because we took the square root, and that'll give us, multiply everything. Oh no, I made a mistake all the way through. I have to go back up there. I am so sorry. I put 6.4. Why did I put 6.4? The leg. Oh no, I had it right. 6.4. I'm so sorry. I'm so sorry. I did have it right. I thought I made a mistake. I thought I needed 1.6. But that's just the diameter. Sorry. I have it correct. So I got this number here when I did that. Double guessing myself, aren't I? So I'm going to have the square root of that, and that's going to give me 1.25 to blah, blah, blah. So we're going to say 1.3 meters per second. All right. So even in a minute, okay, times 60, think about that speed. And then per hour. Wow, that is massive, very fast. So there you have it. That's our section. Don't think I did too many mistakes on the math because I double checked and used what they had. Oh, yeah. So we are good to go. I'm sorry I wasn't in class, but I will get better. Thank you for listening.